Sorry for the slightly late start, but we may very well compensate for that by early finish. Okay, so the point of today is to go through the practice test. Some of you may have taken out already, but what I want to do is go for these, and I just have it downloaded as a PDF, so I will post that after class along with this video. And so the idea is to make sure that you go into this having some idea of how to approach each one of these problems. And for a practice test in my labs, you have a unlimited number of attempts. So if you've been going through that and making some minor mistakes, please try again so that you have your rhythm down to carry out the same thing, but with different particulars on the real test. Okay. Okay. So I'm just going to go through these 8 problems one by one. So the first one is just going to deal with matrix arithmetic. Matrix addition, multiplying a matrix by a scalar, and matrix multiplication using given matrices, in this case A, B, C, and D. Scalar multiplication is nothing more than just multiplying every entry of a matrix by a given scalar. That's what happens in this case, where here we have a matrix A, and then you're multiplying by -3, so you're just scaling each entry by that value. Matrix addition, also entry-wise. So the sum of 2 matrices, you're just adding corresponding entries of those 2 matrices, so the matrices you're adding or subtracting must be the same size. By contrast with matrix multiplication, like here we have matrices of C and D that are 2 by 2, and then A and B are 2 by 3. Rows is always first, so 2 rows, 3 columns. So A and B are both 2 by 3. So one of the products that is asked for is A times C. Order is essential here. So for this product to make sense, the number of columns in the first matrix, so 3 in this case, must equal the number of rows in the second matrix, which in this case is 2. Since there's a mismatch in this case, A times C is not defined. That operation does not make sense. C times A would work because C has 2 columns and A has 2 rows, so you could compute that product. Whereas a product of C and D that's also required in this problem is valid. So anytime you have 2 square matrices of the same size, you can always multiply them. What is asked for? Like, okay, since the operation C times D is valid, to go ahead and actually compute that. So unlike addition, that is component-wise, matrix multiplication is not. So since it's C times D, then you're going to work with, in each entry, you're going to work with a row of C and a column of D. So for example, the 1, 1 entry deals with row 1 of a first matrix, column 1 of the second matrix. So you do 1 times 4 plus 2 times -1. So 4 minus 2 would give you 2. So that would be the first entry of a 1, 1 entry of a product. Row 1, column 1 would give you 2. Whereas to get the entry in row 1, column 2, you're working with the first row of C and the second column of D. So you have 1 times 6 is 6, plus 2 times 5 is 10. So you get 6 plus 10 is 16 as the entry in row 1, column 2. And you keep going. So the entry in, so remember this, the entry in row I, column J of a product comes from working with row I of a first matrix, column J of a second matrix. And by working with, I mean multiplying corresponding entries and then adding them all up. It can be thought of as a dot product. It's a dot product of row I of a first matrix with column J of a second. And that's why they have to have the same number of entries to be able to carry out that operation. All right, so this first problem is all about just basics of matrix arithmetic. Okay. The next problem is also about a matrix arithmetic, but of a different sort, working with vectors. So vectors in the linear algebra world are always thought of as columns. So U and V are given to be column vectors. So in this case, each of them has 3 rows, 1 column. So then U transpose V. So when the first vector is transposed, that's a dot product. So U transpose V is where you would make U into a row, and then V is still a column. So when you multiply them, you're again multiplying corresponding entries, the minus 9a plus 3b minus 5c, and adding them all up. So that's the scalar or inner product. And inner product might be easier to remember because the transpose is on the inside. And when everything is real, as is the case actually in all of our problems in this class, the inner product or dot product is commutative. So U transpose V and V transpose U are the same. By contrast, the outer product, and you can remember that because the transpose is on the outside. The result of that, as we can see here, is a matrix, and the outer product is not commutative. So UV transpose is not the same as VU transpose. And the easiest way to remember how to carry out a outer product is this. Like in this, here we have UV transpose. Notice that if we look at U, minus 9, 3, minus 5, every column of a product, outer product, has that vector. Minus 9, 3, minus 5, minus 9, 3, minus 5, and so on. But what is it multiplied by? The elements of V. So the elements of V are A, B, C. So here we have U times A, U times B, U times C. So each column of an outer product is equal to the first vector times an element of the second. And you go through the elements of that second vector in order. Similarly, VU transpose. V is ABC. So what do we have here? ABC, 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 multiplied by the elements of U in order. So minus 9V, 3V, minus 5V. Okay, so if you remember the pattern of the outer product, then you can come up with that outer product quickly. This problem is about the properties of a transpose. That the transpose of a product, ABX in this case, is equal to the product of a transposes, but in reverse order. So that's something to apply here to get the order straight. these next problems get into the inverse. So here you're asked to compute select columns of the inverse, not computing the whole inverse. So for instance, if you want to compute the second column of the inverse, you would do an augmented matrix where you have A followed by second column of identity. Here we have second and third that are both desired. So that's why you can take both columns, E2 and E3, and slap them both on the edge. And then so then you can go ahead and solve that. That's just by doing row operations on A along with E2 and E3. And once you get to echelon form, then you can solve for the elements of a second and third column that way using back substitution. If you look at these other choices, just like this first part being multiple choice, here we actually have it backwards. So here is a solve the equation AE2 equals B for E2. Well, E2 is the second column of identity, so E2 belongs over here in the right-hand side. What belongs here to A is the solution to that, and that would be the second column of the inverse. So they're trying to throw you off here in their distractors or in their multiple choice questions, that you could get second and third columns by solving a system involving A, but not these systems because they have the E2 and the B backwards. This choice, it would get you the inverse, except notice it says find a second third columns by inverse without computing a first column. If you row reduce the augmented matrix A and all of identity, that will give you all of A inverse in first column included. But then that's, if you only want second and third columns, you don't care about the first one, then that's wasted effort there. So this is the ideal approach. And then with that approach in mind, then you go ahead and actually solve for these second and third columns. And it's from an efficiency standpoint, it's best to work with one augmented matrix. That way, you're only, if you did AE2 and AE3 separately, that would also give you the correct result. You would actually apply the same row operations because the row operations are dictated entirely by A. So you might as well just have both of these in the augmented matrix and do it all at once. And how you go about it for row reduction. So two ways to look at it that are equivalent. One is you get it to echelon form, and then use back substitution to solve each system to get each column of the inverse. Or you can reduce A all the way to reduced echelon form, in which case you'd have identity over here and the two columns of the inverse over here. Again, mathematically, you're really doing the same thing. It's just a different point of view. All right, so here we have this given matrix that represents flexibility, and task is to compute the inverse. So to compute the inverse, you would use one of the approaches that I mentioned from the last problem. If you form an augmented matrix, beginning with D on the left, and then identity matrix, so all of identity matrix, 3 by 3, on the right, and then carry out the row operations to get reduced echelon form of D, then the identity matrix would be transformed into the inverse that we see here. So what they require in this problem is that, okay, for the application part, okay, a list of forces needed to produce this deflection of 0.07 in the third point, 0 deflections at the other point. So what this means is you're taking the inverse and multiplying it by a vector described by these deflections. So your vector you're multiplying by, in this case, has a 0.07 in the third component, and then 0 in the first two components. So now that's a vector, 0, 0, 0.07. So that's 0.07 times E3, the third column of identity, which is 0, 0, 1. So that would amount to taking the third column of the inverse and then multiplying it by 0.07. So that's another way to look at it. But if you carried out the matrix vector product, so D inverse times the vector that describes these deflections, that's what it would amount to, taking just the third column and scaling it by this. Okay, here we have a linear transformation from R2 to R2. Show that T is invertible. So the way you show that T is invertible is you get the standard matrix for this transformation. So the coefficients here give you the first row. The coefficients here give you the second row. So the standard matrix in this case would be 5, minus 9 in the first row, and then minus 5 and 6 for the second row. So if you use a formula for a 2x2 determinant of a matrix, or determinant of a 2x2 matrix, then in that case that would give you minus 15, because it's 5 times 6 is 30, minus 9 times minus 5, so that's 45. So 30 minus 45 would give you minus 15. So it's in the notes, like the formula for the determinant of a 2x2 matrix. So it's AD minus BC. And what's also given in the notes is a formula for the inverse of a 2x2 matrix. So if you take the inverse of a 2x2 matrix described by this transformation, that is the standard matrix of the inverse. And for a 2x2 matrix, the formula is you swap the diagonal entries, you negate the off-diagonal entries, and then you divide by this determinant. And that's what gives you the coefficients of x1 and x2 here. So the standard matrix of the inverse is the inverse of the standard matrix.
Dr.
Yep.
Isn't there supposed to be a 2/3 on the last part?
Wait, here?
Yes.
Okay, let's see. So if we do what I described earlier, we swap the diagonal entries, and then you negate the off-diagonal entries, then you would have 6, 9 in the first row, and then 5, 5 in the second row. Yeah, because since the determinant is minus 15, the only way you would have a 2/3 is from having a 10 here, which you're not going to have.
Well, is there a 1/3 there?
Sorry, what?
Why is there a 1/3 there?
Okay, because, all right, so if you, again, swap the diagonal entries, that's a 5 and a 6. Negate these entries, a -9 and a -5. So your inverse matrix is going to be, based on that procedure, it'll be, if I'm going, so first row would be 6 and 9. Second row would be 5 and 5, but all of that's divided by -15. So then you have 5 over, so in the second row you have 5 and 5. Divided by -15 would give you -1/3, -1/3. So it's just from the formula for the 2x2 inverse. And I want to see if it'll let me add to this. Okay. So we'd have minus, come on, okay. Minus, sorry, this is very slow to do for some reason. So -1/15. So 6, 9. So I'm basically like typing out the inverse in this case that the formula would give. Okay, let's see if it'll let me move this. I guess I can add spaces. Okay, so right here, this 6955 times -115, that is the inverse. Using the procedure I described, where you swap the diagonal entries and you negate the off diagonal entries. And so working this out gives you these.
Mm. So working those out. So that's why there's a 1/3 at the end.
Yeah, and that's why both of these are -1/3. And so type the rest of it out just so it's easier for everyone to see. Okay, so it's easier to see in this format, just taking the coefficients from here. And that's where you can see, okay, swap the diagonal entries, negate the off diagonal entries, divide by determinant. Right. Any further question about this one? Okay. Here, finding a vector that's in the null space of A. Whoops. And a non-zero vector in a column space of A. Actually, column space of A, that one is really quick. You just can pick any column. Because really, column space of A is a set of all linear combinations of the columns. So you can pick a trivial linear combination where it's 1 times one of these columns and then 0 times the others. So here we just filled in the first column. That's all it takes for that one. Null space of A takes more work. what you need to do is you're solving a system AX equals 0. So you use row operations to bring this matrix to echelon form, and then you're going to have free variables. I believe for this particular matrix, you might have 2 free variables. So what you need to do is you need to set your free variables to something other than just all zeros. So make sure that you pick something non-zero for one of them, and then if for example, if x3 and x4 are free variables, and you pick something for that's not all zeros, and then you solve for x1 and x2 in terms of your free variables, so using substitution, and that'll give you a vector that belongs to the null space of A. So that's the procedure to follow in that case. I mean, these subspaces, like any subspace, have infinitely many vectors, but you're just needing to pick out one. Actually, one thing I'm going to try real quick. 232 minus 7 minus 8 minus 9 minus 219, and then 40 minus 8 and 4. Okay. I'm doing a row reduction real quick in another window. Okay. So I'm going to show you, as I can type here. Okay. Wait. Echelon form for this matrix, we were to carry out the row operations to get rid of these entries below the diagonal. Okay. So what you get is, well, the first row is not going to change at all. And then the second row will be 0, 1, 2, minus 3. That's just for whatever you chose for this matrix. Okay, and then for third rows, all zeros. Okay. So x3 and x4 are free variables. So here we have an equation. X2 is equal to minus 2x3 plus 3x4, because these terms will get moved to the other side. So then once you pick values for x3 and x4, because they're free variables, you would use this equation to solve for x2. And then here we have an equation that describes x1 in terms of x2, x3, x4. So you can work it out in terms of those to complete your vector that's in the null space. So I'll just put that in here. So x2 is equal to 2x3, or minus 2x3 plus 3x4. Then you also have x1 is equal to 3x2 minus 2x3 plus 7x4 all over 2. Where x3 and x4, again, are of your choosing. Make this a little easier to read. All right. Okay. Last problem is a quick one involving a dimension theorem. So the dimension theorem says that the rank of a matrix plus the dimension of its null space, also known as nullity, has to equal the number of columns in the matrix. So the matrix given here has 8 columns. Now, the subspace of all solutions of Ax equals 0, that is the null space. I'll just make a note of that here. Come on. Okay. That's what's being described here. So the null space has a base consisting of two vectors. So the dimension of a null space is 2. So then you subtract that from the number of columns of 8, and what's left over, that has to be the rank. So that's why the rank is 6. Okay, so now that I've come to the end, does anyone have questions about any of these problems? Going once, going twice. Okay, I'll post this with my little annotations in Canvas along this video. So I'll go ahead and stop recording at this point.